Hello everyone. Today we're going to revisit the Atwood Machine problem, but now we're going to use the concept of work to solve it. Previously we used forces to find the acceleration of the system. Now we have to find the final velocity of the system. This one's asking just for mass 1, but the system is going to be the same, right? And let's get right to it. It says, a light inextensible cord passes over a light frictionless pulley with a radius of 5.6 centimeters. It has a 22 kilogram mass on the left and a 5.1 kilogram mass on the right, both hanging freely. Initially, their center of masses are a vertical distance 4.5 meters apart. The acceleration of gravity is 9.8 meters per second squared. If the system starts out from rest, how fast is the 22 kilogram mass moving when it hits the ground? Ignore air drag. Okay. So like I said, we're going to use the concept of work to solve this problem. More precisely, net work. Well, we know that net work, because of the work energy theorem, net work equals the change in kinetic energy. And we also know that we use net work when we have more than one force doing work onto the system. In this case, we have two masses, right? And both masses, because they are on planet Earth, they have weight. Don't forget that weight is a force. So work done, net, for this case, is going to be the work done by mass 1 plus the work done by mass 2. That's how we're going to solve this problem. Okay, now let's write down the given. Before we do that, let's highlight things that are important. The fact that we have an inextensible cord and a frictionless pulley makes this problem very simple because we don't have any non-conservative forces. Furthermore, we have no air resistance. Again, no non-conservative forces. That means we can use this equation. We don't have to include the work done by friction, work done by air resistance, because when those are included, the math gets very complicated. We don't have time for that. The 5.6 centimeters has no use for this method of solving the problem. Maybe we'll use it in the future, maybe not. Anyhow, we have a 22 kilogram mass on the left and a 5.1 kilogram mass on the right. And those I will label mass 1 for the 22 kilogram mass, and then mass 2 for the 5.1 kilogram. Let me make that 2 a little better. Okay. And then their center of masses are a vertical distance 4.5 meters apart. That is very, very important. We know acceleration due to gravity is 9.8 meters per second squared. System starting out from rest. And we have to know how fast, that is velocity, right? How fast deals with velocity. Okay. Now let's write down the given. Let me make that line a little better. There you go. So we have mass 1, 22 kilograms, mass 2, 5.1 kilograms. We have a distance of 4.5 meters. And the distance is going to be the same for both masses because let's say this is ground level, right? Let's say this is ground level over here. So when is that? I think that's a little. There you go. So when this mass hits the ground, it's going to move 4.5 meters. So although we have from the center of masses, this distance over here is also 4.5. It's the same. Okay, it's the same. So when this one hits the ground, mass 1 hits the ground, this one moves up, the same 4.5 meters. So the distance is the same. We don't have distance 1, distance 2. It's the same distance. Distance is fixed. For most problems with work, guys, distance is always fixed. Don't forget. Okay, and then we have acceleration of gravity, which is 9.8 meters per second squared. And we have to find final velocity of the system. Don't forget that the final velocity of mass 1 is going to be the same as the final velocity of mass 2 because they're connected by the cord, and the system moves because of mass 1. This one moves down, this one moves up. That's the explicit given. Implicit, well, we know that the system starting out from rest. That means the initial velocity is 0 meters per second. And I think that's it. Well, I'm sure some of you are thinking about another variable, and we'll deal with that later. So let me write down the equation first, and we'll go back to the given. So I'm going to, although I'm going to use, but you know, yeah, I'm going to rewrite. Sorry, that was a lot of jibber jabber. I'm going to rewrite these two equations because I'm going to use them both. So net work is equal to the change in kinetic energy. This one I'm going to use last. And net work is equal to the work done by mass 1 plus work done by mass 2. But we know that the equation for work, when we have one force, so we're considering one force first, and then, one work done first, and then the other work. So when we are considering one force, work is equal to force times distance times the cosine of theta. Okay. Let's think about work done by mass 1. What's the force doing the work? Well, this mass is falling, it's moving down because of its weight. And we know that weight, the equation is mass times acceleration due to gravity. And I'm going to trace the direction of motion. Right, so this is going to move like this, down. And this mass is going to move up. Let me change color for this one so it looks a bit more visible. And this one's going to move like this. Okay. Now, the weight of mass 1 points down because gravity, force of gravity, always points down. And although this mass is moving up, well, its weight is still down, right? Because gravity is always down. Doesn't matter if the system moves up or down, weight always points down because gravity points down. The force of gravity points down. Okay. So that means the work done by mass 1, force is weight of mass 1, that is m1 g. Distance is the same. Now what's theta, right? In this case, theta 1 for mass 1. So theta, let's try that again. It's very ugly. Times theta 1. Think about it, guys. What's the angle between this vector for weight and the direction of motion? Well, you can't draw anything, so theta 1 is 0 degrees. Okay. You may say, oh, same thing for theta 2. Man, I can't draw a 0. But theta 2 is different because this force is pointing this direction. Direction of motion is moving up. So you can draw half a circle between this force and the direction of motion. We also said if a force is going against the motion, so weight is down for mass 2, but the motion is up, that means this mass is doing negative work. This weight for mass 2 is doing negative work. That means theta 2 is 180 degrees. That is very important. If you have both of these as 0, the answer is not going to be correct. So let's simplify this equation. So work done for mass 1 is going to be m1 g d, because the cosine of 0 is 1. And we know that the cosine of 180 is -1. Therefore, the work done by mass 2 is going to be negative m2 GD. Because the cosine of 180 is -1, -1 times m2 GD is negative m2 GD. Okay. So now we can find the net work done on the system. That's going to be net work done is equal to m1 GD. I know it says plus, but it'll be plus a negative, so I can just say minus work done m2GD. I can factor out GD just to make it look better. So there you go. GD M1 minus M2. Okay, that's the net work done. I could find the net work done using decimals, but I'm going to keep using algebra. Again, if you want to get the work done, by all means you can do that. I'm not going to. Now I'm going to deal with this equation, okay? So in this case, we have net work is equal to the change in kinetic energy. So that means kinetic energy final minus kinetic energy initial. Well, we know that the initial kinetic energy of the system is 0 because both masses start from rest. But if you don't see it, that's okay. Let's write our equation. One thing to note is that the energies, kinetic energies of the system, are based on two masses. So for kinetic energy final, we need to account for the kinetic energy final of mass 1 and mass 2. Same thing for initial kinetic energy, which is to say 1/2 m1 b final squared plus 1/2 m2 b final squared. I should have used parentheses. These two equations represent the kinetic energy final of the system. So actually let me add parentheses. Minus 1/2 m1 b initial squared plus 1/2 m2 v initial squared. But we know that the initial velocity for both blocks is 0, so therefore there's no initial kinetic energy. These two cancel. So our equation simplifies to the sum of the kinetic energies. So the net work is equal to 1/2 m1 b final squared plus m2, wait, I forgot the 1/2. I'm getting ahead of myself. 1/2 m2 b final squared. Now we can factor out the 1/2 and the velocity final, right? Because that's what we're looking for, velocity final. Let's factor out. So this will look, net work is equal to 1/2 velocity final squared times m1 plus m2. So now let's get rid of this 1/2. Multiply times 2 on both sides. So I'm going to have 2 times the net work is equal to velocity final squared times the sum of the masses. Now I'm going to divide by the sum of the masses. And whatever I do to one side, I have to do to the other. And then to get rid of the square, I just take the square root. So I'm going to write my equation. Velocity final is equal to 2 times the net work divided by the sum of the masses. Don't forget to take the square root. And if by this point you already have the net work, you just plug in the number. But for now I'm going to use this one over here, GD, M1 minus M2. So my final velocity is going to be equal to 2 times GD M1 minus M2. There you go. That's divided by the sum of the masses, M1 plus M2. And then you take the square root of that. Now let's plug in our numbers. So velocity final is equal to 2 times 9.8 meters per second squared times 22 kilograms minus 5.1 kilograms. Again, if you decided to, oh wait, I forgot the distance. If you decided to get the net work done in joules, part of this step, instead of having this that I'm editing, you would have just a number in joules. Right? Instead of this, you would have a number in joules, but you'll get the same answer at the end. Divided by 22 kilograms plus 5.1 kilograms. Let's see what decimals says. Okay, so this was the procedure we used for the with conservation of energy, and it looks like we're gonna have exactly the same numbers, right? I think so. 2. Yep, they're gonna be the same numbers. 9.8 times 4.5 times 22 minus 5.1. Close parentheses, divided by 22 plus 5.1, and yep, exactly the same number. One thing I should point out, make sure this division, the denominator, is inside the square root, right? Sometimes, for some reason, you guys leave the whatever's here outside of the radical. You don't want to do that, okay? So 7.42, I'm going to round to 2 decimals. That is the final velocity of the system. We use 2 different methods. This one is with energy conservation, and this one is with work. Whichever you like best, use it. That's it.